What if I told you that one of the most fundamental building blocks of digital memory, a 1-bit memory cell, can be created using a simple 555 timer instead of complex microchips? Hey guys, in this video we're going to turn this tiny timing IC into a powerful storage device that can actually remember a logic state even after you stop pressing the switch. Stay tuned to the second part of this video where I'll explain how this circuit works. I've packed my favorite 555 timer projects into a free ebook. Yep, totally free. Don't miss it. Click the link in the description to get yours. Here are all the components you need to set up this circuit. 9 jumper wires, 2 10 kilo ohm resistors, 1 1 kilo ohm resistor, a battery holder with 4 AA batteries for the power source, 1 555 timer IC, 2 push button switches, 1 red LED, a breadboard to connect everything together. The 555 timer IC comes with 8 pins. There is a notch or a dot on the chip's body. Pin 1, located at the top left, serves as the ground or ground supply. Pin 2 is trigger. It is used to start the timing interval in both monostable and astable modes. Pin 3 is output. It delivers the result of the timer's operation based on its mode, either monostable, astable, or bistable. Pin 4 is reset. It is used to reset the 555 timer's internal flip-flop. Pin 5 is control. It allows you to control the threshold voltage levels that the internal comparators use to set and reset the flip-flop. Pin 6 is threshold. It monitors the voltage of the capacitor connected to the circuit. Pin 7 is discharge. It controls the charge and discharge cycle of the timing capacitor. Pin 8 is VCC. It is responsible for supplying the power to the IC. Let's set up the circuit step by step. Begin by positioning the 555 timer IC on the breadboard. The pins are numbered counterclockwise, starting from the top left corner. Refer to the later circuit diagram if you have questions about the circuit connections. Insert the 555 timer in the middle of the breadboard. A jumper wire connects pin 1 or ground to the negative rail. A jumper wire connects pin 8 or VCC to the positive rail. Bend the ends of a 10 kilo ohm resistor. Insert the 10 kilo ohm resistor to pin 2 or trigger in the negative rail. Bend the ends of a 10 kilo ohm resistor. Insert the 10 kilo ohm resistor to pin 4 or reset in pin 8 or VCC. Bend the ends of a 1 kilo ohm resistor. Insert the 1 kilo ohm resistor to pin 3 or output in a few rows below the 555. Insert a red LED into the same row as the resistor and the negative rail. The cathode is in the negative rail. Insert a jumper wire into pin 6 or threshold in the negative rail. Insert a jumper wire into pin 4 or reset in a few rows below the 555. Insert a push button switch into the same row as the jumper wire. Insert a jumper wire into the same row as the push button and the negative rail. Insert a jumper wire into pin 2 or trigger in a few rows below the 555. Insert a push button switch into the same row as the jumper wire. Insert a jumper wire into the same row as the push button and the negative rail. Use a jumper wire to link both sides of the negative rail. Use a jumper wire to link both sides of the positive rail. It's time to connect the power supply. Insert the positive lead to the positive rail. Insert the negative lead to the negative rail. Press the bottom push button to turn on the red LED. Press the top push button to turn off the red LED. We have successfully completed the circuit. Let's dive into the circuit and break it down step by step. This circuit is using a 555 timer purely as a 1-bit memory cell or latch. Instead of running it as an astable or monostable timer, we're only using the internal flip-flop of the 555, with one button to set the bit and another button to reset it. The LED simply shows whether that bit is currently a 1 or a 0. The power source is a 6-volt battery. Pin 2 is the trigger input. A 10,000 ohm resistor, R1, connects from the 6-volt rail down to the node that goes into pin 2. This means that when nothing else is happening, pin 2 is held high at 6 volts through R1. That same node is also connected to one side of the set push button. The other side of the set push button goes to ground. So, under normal conditions, the trigger input sits at a logic high level because R1 pulls it up. When you press the set button, you momentarily connect that node to ground, dragging pin 2 very close to 0 volt. Inside the 555, the trigger pin is tied to a comparator that looks for voltages below 1/3 of the supply. When pin 2 falls below about 2 volts, that comparator fires and sets the internal SR latch. When the latch is set, the 555 output or pin 3 goes high. The key point is that the latch remembers this state. Once the trigger has gone low long enough to set it, bringing the trigger back high again does not change the output. So after you release the set button, pin 2 returns to 6 volts through R1, but the output stays high. That is why this behaves as a memory cell. Pressing set stores a 1. Pin 6 or threshold and pin 7 or discharge are not used for timing in this design. They are left disconnected from the external components, so the classic RC timing behavior of the 555 is disabled. Normally, pin 6 watches a capacitor and resets the latch when the capacitor voltage rises above 2/3 of VCC, while pin 7 discharges that capacitor. Because no capacitor or resistors are attached here, those internal parts never act, so the latch will not automatically reset itself with time. That's exactly what we want. Once set, it should stay set until we explicitly reset it. The reset function is handled by pin 4. Pin 4 is the asynchronous reset input. If it is taken low, it immediately clears the internal latch and forces the output low, regardless of what the trigger or threshold are doing. In this circuit, pin 4 is held high through another 10 kilo ohm resistor, R2, connected to the 6-volt rail. That keeps the 555 enabled during normal operation. The reset push button is tied between pin 4 and ground. When you press the reset button, you pull pin 4 down close to 0 volt, and the latch inside the 555 is cleared. As soon as that happens, the output at pin 3 drops to 0 volt. When you release the reset button, R2 pulls pin 4 back up to 6 volts, re-enabling the latch, but it remains in the cleared state until you press set again. That is the other half of the memory behavior. Pressing reset stores a 0. Pin 3 is the 555 output. It feeds a 1 kilo ohm resistor, R3, which in turn feeds the LED. The LED's other terminal goes to ground. When the output is high, current flows from pin 3 through R3 through the LED down to ground. The LED lights up, showing that the memory cell is currently storing a 1. The value of R3 limits the LED current to a safe level. With 6-volt supply, a 1 kilo ohm resistor keeps the current on the order of a few milliamps. When the output is low, there's essentially no voltage across the LED resistor series path, so almost no current flows and the LED is off, indicating a stored 0. Pin 5, the control voltage pin, is left unconnected in this diagram. That means the internal reference thresholds stay at their default values, 1/3 and 2/3 of VCC. In digital logic terms, the circuit stores 1 bit of information, which is why it's called a 555 timer 1-bit memory cell. I hope this video has shown you how to make a 1-bit memory cell circuit with a 555 timer. Want to dive deeper into 555 timer projects? Grab my free ebook packed with awesome circuits and ideas. Just click the link in the description to download your copy now. If you found this video helpful, give it a thumbs up, consider subscribing for more electronics tips and tutorials, and hit the bell icon to never miss an update. Thanks for watching, and I'll see you in the next video.